on season 4 this morning, and we are going to be talking about solving Arctic cloud mysteries. I am with Dr. Chris Polashenski. I'm going to be able to say your name, I promise. Dr. Chris Polashenski. And he is an Arctic research geophysicist. Roy Hessner, he's an Arctic engineer technician. And Tricia Nelsen, Arctic research physical scientist, all with the Cold Regions Research Laboratory, otherwise known as CRREL. And Nathan Kurtz, he's a NASA chief of the Cryospheric Sciences Laboratory. Good morning, everyone.
Good morning.
Good morning.
How are y'all this morning?
We're doing great.
Doing great.
Great. You know, in the South, we have to say, how y'all doing? So, before we dive deep into the subject matter, I would love for you guys to tell me about yourselves, your background, and your roles at Arctic and NASA. Dr. Polashenski, can you start us off?
Yeah, I'm Chris Polashenski. I work as a research geophysicist for Arctic CRREL, the Cold Regions Research and Engineering Laboratory portion of Arctic. And here I've spent most of my career focused on understanding sea ice in the Arctic. I'm primarily a field scientist. I've spent a bit more than 4 years of my life actually out in the Arctic in remote places, camps, doing research activities over the past 20 years or so. And at CRREL, most people know me as the resident expert on sea ice.
Okay. Roy?
Hi, I'm Roy Hessner. I'm an engineering technician for CRREL. I've worked here for 4 years. Basically, my responsibilities involve setting up all the sensors and electronics equipment for the scientists to collect data. And I also lift heavy things. I spent 30 years on active duty in the Marine Corps, specializing in data communications and electronics maintenance. So I'm here at CRREL just for the adventure.
And I believe you guys have adventure. So, Tricia, you're next.
I'm Tricia Nelsen. I'm a research physical scientist at CRREL, and I focus on terrain characterization of Arctic environments using remote sensing methods. So I've worked on sea ice a bit, permafrost a bit, and snow a bit, and using all the same methods from satellite and drone imagery. And I've been at CRREL for about 5 years now.
Okay, Nathan.
Hi, I'm Nathan Kurtz. I'm a research physicist at NASA, specifically NASA's Goddard Space Flight Center, just outside of Washington, D.C. I've been here for almost 20 years. I'm presently the chief of the Cryospheric Sciences Laboratory, so I lead the studies that NASA does of the ice-covered regions. I'm also the deputy project scientist for NASA's ICET-2 satellite mission. So it's a laser in space studying properties of the Arctic, the Antarctic, all over the globe, again, using the laser altimetry. I've primarily worked with remote sensing data, like satellite data. I've led many aircraft campaigns to the Arctic, so I also use a lot of aircraft data. But trying to use advanced technology methods to study the Earth and the ice on the Earth.
All right, sounds great. Thank you guys so much for telling me about yourselves, and everyone will understand now the collaborative impact of what we're going to talk about today. And again, the theme for today is solving Arctic cloud mysteries. And so when most people think of NASA, they think of space exploration and rockets. But we're here today to talk about NASA's ARC-6, which is a project centered around Arctic sea ice melt. What exactly is this research program, and why is it important?
I can answer that. So ARC-6, it's an acronym, as NASA always uses acronyms. It stands for the Arctic Radiation Cloud Aerosol Surface Interaction Experiment. So the overarching goals are really to study things like clouds, sea ice, aerosols, so particles in the air, and how that's affecting the radiation balance in the Arctic especially. Because the Arctic has really been warming and changing, the radiation environment's been changing quite a bit recently. And so, I mean, many people think of NASA as just a space agency, space exploration, but NASA has a significant Earth science component. So we're using advanced technology. We're using satellite methods to look at the Earth from space. And so space gives us this really amazing perspective of what's happening on the whole of the Earth. And so NASA has a whole fleet of satellites that are measuring different properties of the Earth all the time, and giving us this broad understanding of what changes are happening to the planet. Some of those changes being, how is the ice melting over places like Greenland, Antarctica, and especially the sea ice that's melting in the Arctic at the present time. So many of NASA's Earth observing programs do involve satellites, but we also use aircraft observations. Reason for that, aircraft gives us a different perspective. You can't put the same instruments on a satellite as you can on the aircraft. And to a degree, you can get more accurate measurements with aircraft. But we also do boots on the ground work. That's where some of our most accurate measurements are going to come from. And so when we have a relatively new satellite in orbit, like with ICET-2, which was launched in 2018, we have to spend time understanding what is that satellite actually seeing, how accurate are the measurements that it's making. And so it's, taking together these pieces of evidence to solve something like a mystery. And so that mystery that we're trying to solve is that we've seen huge declines in the Arctic sea ice. So almost half of the ice in the summer in the Arctic has now been lost since we've been observing it since the late 70s. So that's almost 3 or 4 million square kilometers of ice that's been lost in the last few decades. And largely driven by that is because Arctic temperatures have been increasing about 4 times the global average. And so that's why we're conducting experiments like ARC-6. So we're trying to find out, what's driving this significantly different temperature change in, radiation environment that the Arctic is seeing compared to the rest of the world. Why is it changing so much faster? And so that involves things like the ice, the clouds, the aerosols, trying to put everything together. And so that's why NASA is involved in a project like this.
So fascinating. So, and here we go. So what role did CRREL play in this mission, and how did the team contribute to the overall effort?
Yeah, for this experiment, what the CRREL team really provided was one component. As Nathan was saying, well, we look at things from space. That gives us a huge view, but the accuracy is a little bit lower. We understand what we're seeing a little bit less. So sometimes he puts the airplane down underneath that to get a closer view, different types of sensors. And then the last type of observations, well, sometimes you just need to go on the ground. There are certain things you can only measure from being boots on the ground. And that's kind of something we're known for at CRREL. Our group's got a lot of experience safely getting to really remote places, being comfortable working in those places, getting really high quality observations, building autonomous systems that can observe in those really harsh environments that we can leave behind and will keep giving us data over the coming months and years after we're there. And so that's really what we were brought in for, was to do that component of this experiment. Since ARC-6 is really about measuring sunlight and infrared radiation, how they penetrate through Arctic clouds to interact with the sea ice on the surface, we need to understand what's going on with the sea ice. The airborne and satellite teams can get snapshots of the clouds up high. They can get snapshots of the surface, but they really need continuous measurements of the radiation balance at the surface. And they really need to see how the ice is growing or melting in response to that energy balance. And you really just can only get those things from on the ground. Now, some measurements, as Nathan was saying about ice thickness, can be made from space with ICESat-2, a laser. But even that depends on knowing how thick the snow is on top of the ice. And that can't easily be measured in space. So we also measured that, the thickness of the snow layer on the surface of the ice, and left behind sensors that would measure that over time. So, with all these different ground-based measurements available, I would say the value of the entire data set that ARC-6 collects, including the airborne and the space-based experiments, gets a lot higher. We have more clues, more pieces of the puzzle that we can put together to understand what's going on. And, the other teams could say the same thing. They're their airborne measurements are not just more valuable from the ground, the other way around works. So the ground measurements that we're taking are also much more valuable because they flew over in the air to provide context as well. And it's why collaboration on these big projects is important. When you get a whole team of different experts looking at the same problem like this from different perspectives, the plane flying over, understanding the structure in the cloud, and then the radiation sensor on the surface saying how much radiation is coming down to the surface from a cloud that has that structure, you can start to put the two pieces together and really understand the system quite a bit better.
So in an article, and again, I loved reading all about this information, but in an article I read, it mentioned that as sea ice melts, more clouds form in the Arctic. Can you explain how this cloud blanket impacts the Earth?
Yes, I can explain that one. So as the sea ice melts and exposes open ocean, the water can evaporate from that open ocean, and the extra moisture makes it into the lower atmosphere. It's fairly likely that that'll increase into cloud cover. And the clouds do two things. First, they act like a blanket, trapping infrared and long-wave radiation near the Earth's surface, keeping it warmer on the Earth's surface. And second, they reflect the sunlight that prevents some of the sun's warming rays from making it to the surface, and that makes it cooler. So these two processes are fighting one another, and that's why the details of the clouds matter. Low fog that the sun mostly shines through warms the surface more than it cools it, but clouds in the winter time in the Arctic when there's no sun actually warm the surface. So Arctic 6 needs to understand not just where the clouds are, but also what the vertical structure is like and how that's impacting the energy balances at the surface. And they just might be the reason that the Arctic is warming so much faster than the rest of the planet.
Wow. So your team engineered and deployed specifically modified buoys for this mission. How did you adapt these buoys, and how do they support this project?
Yeah, I can take that. This is Chris. The buoys for the Arctic 6 mission were a version of what we call our sea ice mass balance buoys. That's something our group's been deploying in the Arctic to monitor change for more than 25 years. These buoys have really been a key to monitoring some of the really big changes that have been ongoing in the Arctic sea ice cover over the past decades as it's gotten thinner and melted away. And of course, over 25 years, we're always updating and refining the buoy technology as new electronics become available and new needs arise. So it's kind of a living program of monitoring the sea ice. And as each mission comes along, in the case of this mission, there's a need to deploy buoys in different circumstances and with different sensors. So for this one, the target area right north of Greenland and Canada is one of the places that has the thickest ice in the Arctic, and we usually don't deploy buoys in ice quite that thick. So we had to modify the buoys to make them longer so that they could go through thicker ice, in this case up to 3.5 meters or around 12 feet thick. We added sensors for measuring incoming and outgoing radiation to focus on what's important for the Arctic 6 project, and to measure the snow depth, and not just at the buoy, but actually at a bunch of locations all over the ice floe. So we were able to add all these additional sensors and add a really cool new low power radio link interface to make it so we could put those snow sensors all over the ice floe, because we had this mothership of a buoy that we've developed and refined over a lot of years. And the really hardest thing in the Arctic is it's really harsh. It's 50 below. The ice is moving and shifting all the time. There's high winds. Finding a sensor package that works, that can communicate out from the Arctic with the really low availability of communications, can conserve power enough to last for a whole year. These are things that have taken us quite a long time. So having that platform that we can then add other sensors to really gives us a lot higher likelihood of success. We're not developing the whole thing from scratch each time.
Right.
In the future, each time we add a new capability like the distributed sensing technology we've got here, now we have a way to inexpensively measure anything else on an ice floe that needs a whole bunch of sensors distributed across a few kilometers of ice, whether that would be under ice acoustics or stress or ice fracture or melt pond formation. we've got lots of ideas for how we can keep using this and adapting it to other projects. And it's very exciting to work with a project team like the ARC6 team that has a specific goal, that then we can engineer the platform we have in a direction that helps that for them.
Well, I mean, even when you said 50 below, I just all of a sudden got a chill. That's awfully cold. Man. I also read where the buoys are described as versatile platforms for adding sensors. Can you share examples of how you've used this flexibility to answer new research questions?
Yeah, Chris touched on this a little bit, but in some ways, the hardest thing in the Arctic is communications, and luckily we've had satellites up there for many years, but that is really the only practical way to get data back from these sensors and the buoys is by satellite modem over the Iridium network. So this requires an expensive transmitter and a large battery to power it. And then you need to have a large buoy hull to house all of this. So those components end up making most of the cost having an observing point. And from there, adding other sensors to the data logger is really not such a big deal. So our basic instrument package tracks whether the ice is growing or melting from the top and bottom, air temperature, barometric pressure, and temperature profile down through the ice. But then for some experiments, we have added salinity and temperature sensors to understand how the upper ocean is heating up and potentially melting the underside of the ice. For others, we've added light sensors beneath the ice to detect how much sunlight is available for algae growth. Acoustic sensors and stress gauges to monitor ice movement and fracture. The list really goes on. And really, we were thinking of the buoy as the center brain and communications node that we know works in the harsh environment at 50 below. And then there's just so much to learn from the Arctic Ocean, where so few observations exist, that we could really keep going as we think of more things that we need to research.
Well, and just like their theme for this season is the collaborative impact, what partners did you work with to develop these buoys? And can you detail the collaboration and how it enhanced the project's success?
Sure. Well, I mean, in addition to working with the NASA team to refine the questions and come up with the right sensor package to put out, we also collaborated with a company called Cryospheric Innovation. This is a startup company that was founded by Cameron Plank and James Whitcomb. These guys were graduate students who worked under my group and got their PhD and master degrees at Dartmouth. Then they decided to start their own company building scientific instrumentation afterwards. And it's been a really cool partnership. They've helped push the technology to new levels and begun to introduce a lot of efficiencies in producing the buoys in greater quantity and at lower cost. And, you know, having them as a company fully focused on making the tool, where I've got a lot of other things on my plate trying to move the research forward, has really been great. I mean, they've improved the reliability of them. They've reduced the cost. And it really just lets me spend my day focusing on analyzing the data and working out what it all means, rather than spending so much time getting the electronics to work and communicate and bring the data back. And I think it's just really been a great public-private partnership that's, you know, saving us money, it's getting better results, and it's moving the science forward faster. And one really cool thing that's kind of come out of it is that they're now able to sell the buoys to other countries' research programs for other things. That's made our partners in the Arctic start to share the burden of monitoring. So, you know, I log onto the Cryosphere website and I get to see that there's been new buoys deployed by the Germans and the South Koreans and the Canadians and the Norwegians and other allies kind of all over the Arctic. And each of those is also contributing to the overall picture of change in the Arctic. The barometric pressure and temperature from them is going into the world forecast models. And so in some ways, by transitioning this technology to Cryosphere Innovation as a company, we've been able to have a greater impact as more buoys are going out as a result of it.
So logistically, deploying these buoys in such a remote part of the Arctic seems like it would be a huge challenge. So can you tell us a little more about these desolate locations and what are the most difficult aspects of reaching those areas?
Sure. Yeah, I don't think of them as desolate. I love the Arctic. I think it's a wonderful place. You get to see polar bears and walruses and seals and whales and things like that while we're working. But it is certainly cold and not for everyone. So yeah, the area where NASA needed these buoys in this particular experiment, it's really hard to get to, like really hard to get to. I think of it as one of the most challenging places to get to on the planet. And I think of that as a guy who spends years of his life in remote places. So, sure you could get there if you fly over it on a jet, like from Frankfurt to Tokyo or something like that. And NASA can get there with their jet aircraft from Patuxent Space Force Base in a couple hours in northwest Greenland. But I'm talking about actually being able to stop and get out on the ground. And the jets need a few 1,000-foot perfectly smooth runway to land, and they can't set down on the sea ice.
Right.
And so, like, you think through your other options. Well, you can get an ice-breaking ship. Well, but not in this part of the Arctic and at this time of the year. The ice is too hard and too thick. You can't drive an icebreaker there. And while a lot of other areas we access with a helicopter, can't do that here. The distances are too great to the nearest place you could get fuel. You just can't carry enough fuel to get there. I mean, there's a few intrepid souls who've gone through this area by dog team trying to adventure to the North Pole, but I'm not quite that rugged, and not all of those folks made it.
Right.
So we get there on an aircraft that you kind of have to go back in time a little bit. We use a de Havilland DHC-6 Twin Otter. It's a short field capable takeoff aircraft. It's first built in 1960s, and they're cool machines. They can fly super slow. They can take off and land in 1,000 feet or less, and you can put skis on them. Plus, they've got like an 800-mile range, much further than most helicopters. So altogether, that gives us the capability to just barely, if we bring extra fuel and use some fuel caches along the way, get out to the area we hope to work in, and be very careful and look for spots to circle around and land on the sea ice. And when I say just barely, I mean it. I mean, the only staffed outposts that support work in this region and have fuel supplies are Eureka and Alert in Canada and Nord in Greenland. The farthest north permanent human settlements in Greenland at Connaught are 400 to 600 miles to the south, and the outposts that we can arrange to get fuel at are all 300 to 400 miles apart. So there's a point en route from one of the stations to the next where we more or less have to complete the flight and can't turn around on each one of the legs. There's a few other fuel caches out in unoccupied camps here and there, but this is really pretty sparsely inhabited place. Right. And beyond even all the logistics of fuel and stuff, there's like the technicalities. We're operating across an international border. Every time we move between Canada and Greenland, we're supposed to hit customs, but there's no customs up there. So in advance, you have to do a bunch of work ahead of time to make it legal to do this. And I have to say, both countries were extremely helpful and went out of our way to accommodate this work, and I'm super grateful for that. So yeah, it's a pretty fun experience getting to work through all these challenges just to get there in the first place.
I think your definition of fun is a little bit different than my definition of fun. So,
and Chris, don't forget to mention that it takes about 36 hours just to get the furthest you can on a commercial flight before we jumped off on our actual mission. And that's just to go literally 1,500 miles as the crow flies from Alaska to where we started. And it was required, just a logistical nightmare.
Wow. Okay, so once you made it to the site, how did the team manage the complex task of landing the planes and installing the buoys on the sea ice under such harsh conditions?
So I'll take this one. This is Roy.
Okay.
So landing is definitely a challenge, as you can imagine. If anybody's ever seen the Arctic sea ice, it's not like an ice skating rink. It's full of pressure ridges, and the ice out there comes from different generations, years as it's freezing and thawing and cracking and all that.
What's a pressure ridge?
A pressure ridge is, Chris, you want to give them the technical definition of a pressure ridge?
Sure. It's basically it's a mountain range out of sea ice. It's where two plates of ice come together and push against each other, and where they're pushed against each other, the ice breaks and pushes up into a great big pile. It's a mountain building in fast motion.
Okay.
Yeah.
Continue, Roy.
Definitely not a nice smooth field of ice to land on. But before that, in the morning, the pilot, co-pilot, and Chris, because he definitely understates his experience in the Arctic, but he's also a private pilot, so he understands all this stuff in great detail. But they spend the morning poring over satellite imagery of the site where we intend to go to make sure the weather's clear, because operating in the Arctic in poor light conditions can be problematic for the pilots and stuff. And they definitely went out of their way to minimize any safety concerns in a pretty challenging environment. Then we fly out to the basic area where we're looking to put the buoy by GPS coordinates, and then once we get there, then we have to start looking at the ice, and so they'll drop down to a lower altitude and start scouting the ice specifically. And again, Chris on his headphones, he's talking to the pilots because again, he's got years and years of experience. Tricia and I were pretty amazed at just like this pretty complex operation, but they're looking for basically a safe piece of ice to land on, which would be probably first year ice, like a lead that opened up that had refrozen, so it'd be nice and smooth, have a little bit of snow on them, but it's got to be old enough and thick enough to support the plane. So we're looking for something somewhere in the range of about 75 centimeters at a minimum to land on. And of course, that site has to be adjacent to multi-year ice that we want to put the buoy in.
Right.
So it's definitely there's a challenge out there. So if the ice looks good, they circle around and they get lower and lower until our pilot Troy is just a master, has a great reputation up there. Everybody who we talked to asked us who our pilot was, and as soon as we said Troy, they're like, "Oh, you're in good hands."
You're good.
Totally, yeah. It's definitely confidence building because I've seen combat, and I was more nervous about landing on the sea ice than I was in Iraq. I'll tell you that.
Wow. So he gets hero status.
Yeah, definitely. So, they would do a couple passes, getting lower and lower. A couple times they would get almost just off the snow, and they would take power off and come back around. So they really would check that prospective landing site out, and then. And again, Chris is talking to them. They're all communicating. They would put the plane down, be very conservative because obviously we're a long way from home. And if they misjudge something, and Chris, we would talk about our safety briefs, and he would his favorite thing to say was, if we knock a nose wheel off out there, I'm like, stop talking about knocking a nose wheel off out in the middle of the Arctic. But he was just kind of emphasizing the point that we're a long way from help. And so we need to be extra sure of everything that we do. So
to make sure they don't do a movie about the adventure.
Right. Yeah, we have no intention of being Hollywood famous.
Right.
We can be Erdic podcast famous, but
right.
we want to be Hollywood famous. So once they felt confident, they would put the plane down. There'd be some bumps, and honestly, they were smoother. I can't even lie. They were smoother landing and taking off on that ice than the Alaska Airlines flights landed on an actual commercial runway. I was really impressed. Those guys did a great job. And the team is kind of a joke. I was usually nodding off before we even took off. It was that smooth. So
that's pretty smooth.
But once we hit the ice, that's when the action actually began. And we were on kind of a clock. Chris wanted us on the ice no longer than an hour. So it was kind of like a pit crew. NASCAR pit crew. As soon as the plane touched down, the door flew open. One of us would jump out, and we have a 2-inch diameter drill on a cordless drill, 2-inch diameter bit, and we would immediately drill right next to the plane to verify the ice thickness for safety of the plane.
Right.
Then once we verified that we were on solid ice and there was nothing that we needed to be concerned about there, then Chris would search out the site that he found from the air, and he would test drill the hole there to verify that the ice was at the appropriate thickness. So we actually have to drill a 10-inch diameter hole all the way through the ice, no matter how thick it is, if we're going to deploy the buoy. And so we're looking for ice that's more than 2 meters, but less than 3.5 meters. or about 7 to 12 feet thick is what we were. That was our target. Once we figured out that the site was good, the plane was safe, the site was good, we would get out the power head and the auger. The auger had two 12-foot flights and drills basically, and we would drill the first 6 feet down, pull it out, we'd put the other 6 feet on, and then we would drill until we broke through, and then we'd pull it out. The buoys are really kind of interesting too. They come in 3 8-foot sections in an 8-foot long crate. So once we got the hole drilled, we pop the lid off the buoy crate, and Chris and I would put the buoy together, and then we would, what do they weigh? Like 125 pounds or so. We would march it over to the hole, stand it up, and then lower it down into the hole. All the instruments are pre-installed. Everything is ready to go as soon as, we have to, the sensors on there, on the top and the bottom are a little fragile, so we have to be careful as we lower it in. And then once it's in place, we flip the switch on, make sure everything lights up the way it's supposed to, and then bury it all up. And while that's happening, Chris and I will be doing that part, and then and Tricia was magna probing. She was taking snow depth measurements, and even the pilot and co-pilot were also helping assemble things. Like I said, it was really kind of a pit crew mentality. Once we hit the ice, things happen pretty quick.
Under the clock, I got it. So how important is it to understand the Arctic's radiator effect on the planet's energy balance? And what role do clouds play in this process?
So I think, sorry, go ahead, Nathan.
Oh, go ahead, Tricia.
I think it's actually one of the most important things for folks to understand, where from something so far away that they don't think they need to understand, but what is happening up there really has a big influence on what happens climate-wise for the rest of the planet. So it might be far away from somebody living in Florida, but it really is going to have a big impact on them. And so it's an area of the planet that in net loses heat to space. But since it has been warming so much more rapidly than the rest of the planet, the Arctic is warming at about 4 times the rate. Its efficiency at getting rid of that extra heat is dropping really rapidly. And that will impact the temperatures on the rest of the planet more than folks mostly probably realize. And clouds are a key part of that process because they are one part of the Arctic system that might help explain why the temperature is increasing there so much more rapidly than elsewhere on the planet. As we mentioned before, they have the potential to act as a very effective blanket, reducing that energy loss, particularly if the type of clouds are just right in the summer or really any clouds in the winter. Nathan, if you have anything to add, feel free.
Yeah, I'd just like to add, from NASA's perspective too, we use satellites to look at all parts of the Earth's climate system. So like Tricia was mentioning that the Arctic is radiating that heat, and that heat comes from the tropics, the equator. It's moving up to the poles. And so when you think of that movement, that's the atmospheric circulating. And so that's what drives our weather. So that drives our weather here, like in the U.S. So again, that's why it's really important to study the climate as a whole, and these different components, like the ice is a component that affects the climate around the world.
This question is, the data from the buoys is publicly accessible. How can the public and researchers and even students benefit from this real-time data?
I can take that. This is Chris. Well, the data is available in real time at cryosphereinnovation.com. And I just think it's some of the coolest data out there. There's a map that shows how the buoys and the ice they're in are drifting. A lot of people don't even know that the sea ice is moving and drifting all the time. The buoys move hundreds or even thousands of miles a year as they work their way across the Arctic, and that alone is pretty interesting to watch.
So people can watch that.
Sure, they can log right on and check out on the website anytime they want to. If you're feeling cold on a winter's day and want to see how much colder it is near the North Pole, well, check it out.
Awesome.
The temperature up to the hour is being reported from one of our buoys up there. And the data is also being fed into other things. It goes directly into the World Meteorological Association system, and there it gets fed into all the weather models. So it improves the forecast. And we've really actually noticed while we do this work, there's so very few barometers, which, barometric pressure is something you can't observe from space. You have to be on the ground to put out a barometer.
Mm-hmm.
That the buoys have a really significant effect on improving forecasts. Like, we go up, we start a campaign, and we note that the weather forecasts are just not very good because we're working with aviation and flying out to all these places. So it's frustrating when the weather forecast is wrong as we're preparing to deploy the buoys. And then we put a big array out, and at the end of the experiment, the forecasts all improve considerably in the region up there. And also, this does have actually a measurable impact on forecast quality all the way down to the lower 48 because, as Nathan said, that this is the connection. The cold fronts that you get in the lower 48 all originate in the Arctic. So, getting their spilling out of the Arctic correct in the models is really key to getting them to show up in the lower 48, 3 days later in the prediction correctly. And then, lots of other researchers are using the buoy data for a wide range of analysis. I like to say that the ice is the truth. It balances out all the processes that impact the energy balance. If the Arctic's losing energy, we grow ice. If the Arctic's gaining energy, we melt ice.
Right.
And just by looking at the timing of when we grow ice or melt ice and how much we grow or melt, we can learn a lot about a particular process and whether a hypothesis is true or not. If somebody hypothesizes that it's the ocean melting the ice and the ocean has gotten warmer, well, it better melt on the bottom. And so, just by having the buoys out to tell you whether the ice is melting on the top or the bottom and when, we can check a lot of hypotheses. There's actually well over 100 scientific papers that have used the buoy data to check a theory, validate a model, conduct some type of analysis. So it's a data set that's it's baseline monitoring, and a lot of people can use it for a lot of different things, some of which we really just didn't even envision in the first place.
Well, and again, thank you guys for what you do. It's so important. Your research is so important. So as we close out, what's a key takeaway from each of you that you'd like our listeners to have from this very valuable conversation? Chris, we'll start with you.
Okay. Yeah, I guess I'd say the key I'd like to take away is the Arctic and what happens in it is actually really tied pretty closely to what you do. That last cold front that came through, it's a good chance it originated in the Arctic. And if the Arctic continues to undergo real rapid change, well, there's a good chance it'll have an impact on the weather and the climate you're used to here at home. And since it's changing so much more rapidly than the rest of the planet, we kind of think the clues for what's in store as the climate changes are probably likely to be found there.
Okay. Roy?
Well, my takeaway is hang out with smart people. I've learned so much from Chris. We've had some pretty in-depth conversations about like the Greenland ice sheet and the Antarctic ice sheet and some things in the positive feedback loop, when ice starts to thaw and all that. And so it's just been really illuminating to me about the impacts. And here in the Corps of Engineers, we're not an activist organization. We have to engineer how we live in this world. But climate change is a big part of that. And so understanding what's real and what's not real and what we hear in the news and what we can, expect in the future. And Chris has been a big part of that, shaping my worldview, and I appreciate that. So hang out with smart people. That happens.
Okay. Tricia?
I think, Chris said it better than I could, but I think just paying attention to what's happening in the Arctic, even if you're in a tropical place, is really important, especially at the rate that sea ice is melting and what we're losing and how that's going to feed back into the rest of the climate for everyone. I think that I feel really fortunate to have gotten to be in one of these places that, as we were flying around, it's harder to find these landing zones so Chris and the pilots were saying, and soon that might not be able to happen. So I feel very fortunate, and I think it's a place where people should be focusing on what's happening and thinking about how it affects their life.
Fantastic. Nathan?
Yeah, I'd like to emphasize, the amazing collaboration and partnerships that, make all this happen. NASA's trying to study the Arctic with, fancy technology and, aircraft overflights, satellites, things like that. But, really being able to partner with CRREL to put these buoys, really helped this Arc-6 experiment tremendously. It dictated our flight lines, where we're flying. It's going to dictate how we're analyzing and understanding the data in such a, fundamentally new way. And so, this comes from us collaborating and working together across federal agencies. So, it's really nice seeing this come together, again, across the U.S. and then partnering with our international partners to be able to go into their airspace, deploy in their within the Arctic or around their different countries. So, we're doing this so that we can understand the planet, what's happening, how this is impacting everyone. And so it's really working together on this it's really good feeling to have.